Hi, and a very good day. For today's session, we will continue discussing on statistical validation and testing procedure. Based on our previous video, we discussed on the strategy on how you can build your models, okay, based on general to specific or specific to general. And the way on how we build this particular model is based on statistical validation and testing procedure. And what if, even though that you do the statistical validation and testing procedure, some of assumption might not be fulfilled by the models, there are several things that you can consider to do, such as you can reformulate the models using different functional relationship. You can select new or you can edit independent variables. But remember, you have to check the theoretical explanation behind the variables, the independent variables that you want to add in your models. And you can also obtain more data points, means that you increase your observation. Okay, maybe the period from 2000 until 2023. Now you can stress more. Maybe you can add 1995 until 2023 as examples. Okay, and also performing some transformation also can help to improve our models, such as log transformation, and we can also reconsider the theory that we use. Okay, and most of the time, even though that there are justification on this particular independent variable effects on the dependent variables, some of the theory might not applicable on certain situation or different country, as example. So you have to reconsider the theory that used as a basis of build when you build the models. Okay, so in our discussion today, I will discuss on several statistical tests that will be used to do the validation. Okay, so means that when we perform general to specific or specific to general, this is the guideline that we use to decide whether we want to retain or we want to exclude the variables. Okay, so we have general fitness of the models, significance of regression coefficient, t-test, goodness of fit, r square or adjusted r square. This is the test. So this is the thing that we want to perform. Heteroscedasticity, okay, Brush-Pagan test, serial correlation. We use W-Watson test to test the serial correlation, and multicollinearity. So remember that we have our test, and we want to test whether these particular models that we built fulfilling the assumption pertaining to the model or pertaining to the error term. So for general fitness of the model, we test on the assumption of the models. Okay, and then also the same as t-test, since that after we get the significant value for f-test for general models, we will zoom in, okay, for each of the variables that we include, whether the significant variables, whether the independent variables significant or not. So that's why for this this is assumption for the models, and for goodness of fit is also for a model, because we want to know, okay, how much our independent variables that we select can explain the changes in our y or our dependent variable. Okay, for heteroscedasticity and serial correlation, this is the assumption towards the error term. We take a look on the characteristic of the error term, whether the error term have heteroscedasticity problem or not. Okay, and we also besides that, we plotting the residual, we can also perform statistical tests such as Brush-Pagan test to check whether there is heteroscedasticity problem or not. Okay, and then for serial correlation also for error term, because we want to see whether the error term across the time period have correlated or not with each other. Okay, for multicolority, so multicolority is your IV, your independent variable. As example, you have x1, x2, x3. Suppose that x1 and x2 they have a relationship or they correlate each other. Okay, what happened when you put x1 and x2 with the same models? They actually contribute the same information to to cause the changes in your y or your dependent variable. And for that particular situation, um, we cannot detect, okay, how much changes that these particular variables is affecting the y, because they now have two like similar variable being added. So that's why we have to make sure that our x1, x2, and x3 is independent with each other, so that there will be no multi-quality problem. So for this, this is we check the assumption pertaining to the model, right? Okay, so let's take a look at the explanation on general fitness of the models. This is basically we use f-test. Okay, we use f-test to test the general fitness of our models. Okay, so how do you know whether whether our model is fit or not? We take a look whether the f test is less than 0.05 or greater than 0.05, and this is basically the result that we want. The f test is less than 0.05. So what are the indicator when the p value for f test is less than 0.05? It means that there is at least one variable that can explain your dependent variable. There is at least one. But which variables that contribute to the in explaining why? Which are the significant variables? After we do f test for general model, now we conduct t test for each of the coefficient. And we also want our t-test, the p-value of our t-test, to be less than 0.05 to indicate a significant effects, okay, towards dependent variables. Okay, suppose that for this step, you perform f-test and your f-test is, the p-value for f-test is more than 0.05. So what you do is you have to reconstruct your models. Okay, you have to reconsider your independent variable, means that you cannot proceed with the next step because your model is poorly fit. So that's why the first step here is very important to see the general fitness of your models. Okay, and then after we perform f-test, okay, we perform t-test, and based on the t-test, we can distinguish which okay which variable is significant. Okay, as example here, if we go to the slide with output here, okay, let's say this is the output. All right. Okay, this is the output. The f-test is this one. The f-test is this one. Okay, the f-test. Sorry. The f-test is this one. Okay, and the p-value for f-test is this one. Okay, so this is p-value for f-test. After we take a look at the f-test and we say that, oh, okay, the p-value is less than 0.05. So what we can do next is we take a look at the t-test here. So this is the t-test that for each of the coefficients. So this is our beta. So beta, the coefficient, the beta intersect with beta naught, beta 1, beta 2, and so on lah. Okay, depending on how many variables are you do you have? So based on this, you can take a look which variable is significant. So you must take a look at the t-test that less than 0.05. So for this particular output, you have this one because it's less than 0.05, and this one, and also this one. Okay, even for this R output, they give you this asterisk symbols where the asterisk is uh, is highlighting the significant levels. Okay, this is significant at 0.01. This is significant at 0.001, and this is significant at 0.05. So we want our coefficient to be significant at least 0.05. If not, we can consider to remove the variables that which is not significant. Okay, so that's about the uh, general fitness of the models, and based on this, we can otherwise remove the insignificant variables. So after this step, since that in our strategy before this, okay, general to specific, we do step by step. It means that when you decide to remove one variables, you will start again with the same statistical validation and testing step. So you have to perform the F test again. Okay, suppose that you drop the one variables and you have to model variables without that particular uh, variables. Okay, I will demonstrate it using R later. Okay, this is just for explaining the concept behind statistical validation and testing procedure. And now we have one thing that we can do to measure the goodness of fit, whereby we can use the R square. Okay, R square can be defined as the measure of total variation in YT that is explained by an estimated regression line. And this particular value is between 0 and 1. Okay, so based on this, we actually have two. One R square, another one is adjusted R square. Okay, the difference between R square and adjusted R square is adjusted R square, it also consider on how many variables you added in your models. So that's why for this particular model, since that we can we have multiple variables in our models, and we want to make sure that the number of variable is also being considered when you perform this test. Okay, we will suggest you to use adjusted R square compared to R square, but we can report both. But be careful when explaining the R square. Okay, R square, when you explain, okay, total variation in YT, it means that, okay, suppose that we take a look at the output in our R. Okay, let's take a look at, the output of our R. Okay, so your R will give you both R square. This one is R square. Okay, I highlight here. This one is the R square, and this one is adjusted R square. Okay, so means that this explain the total variation, means that how much your particular variable here, 1, 2, 3, 1, 2, 3, 4, four variable here can explain your YT. So if you want to explain about the R square, okay, suppose that we use adjusted R square value 0.96. You can state that, okay, 90 we use percentage to explain, 96.23% of the total variation in YT is explained by the IVs. Okay, so means that um, okay, while 3.77% is explained by other factors. Other factors. Okay, it means that when you take a look at this, uh, even the total variation here, it means uh, how much information, okay, your variable is explained. So 96.23 is quite high. Okay, so that's why um, we can use this R squared to justify the goodness of fit of our models. Okay, right. So that's about our R square, and next is heteroscedasticity. Okay, one of the assumption of pertaining to the error term is we have to make sure that our error term is remain constant all over time. So for what we want our model to have is actually uh, this one lah. Okay, we want our model to have uh, this characteristic. Okay, and how do we know whether the error term is the variant of our error term is homoscedasticity or heteroscedasticity? Okay, homo here means constant, hetero here means different. Okay, not constant. Okay, so how do we know is we can check the the characteristic of our error term by plotting the residuals. Okay, means that you have the uh, the fit, the fitted observation and the actual observation. You minus to get the error term, actual minus fitted, and then the difference of the models too. You plot it and you take a look whether there is any patterns or not. Okay, so we want our error terms not to have patterns like this one lah. Okay, so this is our desired error term. Okay, and suppose that there is a pattern in our models, you have to consider to remedy the problem. Okay, remedy the problem. Okay, besides we take a look at the plot, we can also use a statistical test, which is Brosh-Pagan test. Okay, what are the remedy of heteroscedasticity? The remedy of heteroscedasticity is you can actually transforming the variables. Okay, transforming the variable means that you can uh, transforming the either the dependent or independent variables to take a look whether it improve the heteroscedasticity problem or not. Okay. All right, and next is about serial correlation. Okay, serial correlation is also pertaining to the error, pertaining to the error terms. Okay, whereby your error term for period. This is for the last period. T minus one is lag one. T minus two is the last two period. Okay, this is the this is ET is the current one. ET plus one is the lead one, the future T plus one, and then T plus two. So if this particular error term have correlate each other, means that they have relationship with each other, means that they have the serial correlation is exists. And another terms that we discussed about the serial correlation when it comes to econometric models, since that our econometric models is across time. We also it also the serial correlation problem also known as autocorrelated. Okay, so if there is a major or serious serial correlation problem, we can uh, we can remove, or we can omit the variables that might cause this serial correlation problem. Okay, and this is one of example where our model is misspecified. We say that if there is serial correlation, the model is misspecified. And the most common type of autocorrelation is the first order autocorrelation, where the previous period have relationship with the current one. So based on this, we can actually take a look on the effect of serial correlation by using this particular relationship. Okay, so it means that they have a certain uh, the ET minus one here, the lag error term, the previous error term, have some sort of a degree of information in explaining the current error terms. So we can take a look at how serial correlation happen when this particular problem exists. Okay, and after we do some repeated substitution, we can reach to this particular general terms lah. Okay, it means that now, since that there is serial correlation, the assumption of error term is remain independent toward each other is not being fulfilled. Okay, because of this particular relationship. Okay, and based on this, previous lag will affect the variance of your the variance of your error term. Okay, remember that the assumption of our models, the error term must constant across the time. So now the assumption will is violated, since that how many k is how many lag, how many previous observation that you have, they have weightage on the variance. Okay, so the variance will keep increasing when the lag is increased. This is example of positive correlation, right? Okay, so okay, so what are the remedy for serial correlation? Okay, the remedy of serial correlation is you can add either the lag of the dependent variables. Okay, you can add either the lag of the dependent variables or the independent variables. Okay, even when we calculate the besides that, okay, you can check the serial correlation by investigating the plot of the residuals. Okay, okay. So take a look at these examples, so that based on this, you can take a look that this is the residuals. Okay, this is the residual, means that the value when you perform the actual minus fitted, and then you plot the residual across the time. Okay, across the time. And for positive correlation, height value correlation we follow with the height value of residual we follow with the height value of the residuals. Okay, some sort of like this. Okay, height value of residual will follow the height value residual if positive. Same as the negative one. Height value negative residual we follow negative residuals. So this is examples of positive correlated serial correlation. And if the value show a negative serial correlation, what happened is, instead of the one that we show you before this, uh, the very low residual we follow with very high residuals, and then very low residuals, and then very high residuals. So this is example of negative autocorrelation. Means that we plot the residual here, the residuals, the error, the error terms, and this is the across the time, the error terms, okay, et across the time. Okay, so that's the difference between positive and negative serial correlation, and we can actually investigate serial correlation based on the Watson test. Okay, when you perform the Watson test, they will give us the value, and we can determine whether they have a positive or negative serial correlation. Okay, so even for this particular definition, like this text say that positive error in one period are associated with a positive error, very high error, and then very high error, and then negative. It means that very high positive, and next is very very high negative error, and then it will follow with very high positive error. So it will become, when you plot the residual across time, it will show a zigzag pattern. So that's a negative serial correlation, right? For this particular test, we want to make sure that the p-value is more than 0.05, or else there will be a serial correlation problem. So this is indicator of whether uh, our data have serial correlation problem or not by using Watson test. Okay, and how to remedy this? We can remedy this um, by include either lack of the dependent variables or independent variable. So that's how we solve the serial correlation problem. Okay, and lastly, multicollinearity. Multicollinearity is when two or more independent variables are related to each other. Okay, are related to each other. So it will be so means that the information, or uh, there will be tendency to contribute overlapping information. All right, and how can you show that this particular multicollinearity problem? You can use this example. Let's say that for this particular relationship, x1 and x2t, x1t is actually the two two the twice of the value of x2t. Okay, means that when we perform correlation test, x1t and x2t will have highly correlated value lah. Okay, and what happened when this particular problem happened, it is rather difficult to explain the relationship between YT and X2T. Okay, when you explain the concept of statistical validation, if there is a mathematical equation behind that, it helps you to understand the concept of what happen if this problem occurs by using some sort of mathematical equation to explain the concept. Okay, so one way to solve this multi-cognitive problem is by while dropping the variables. Okay, by dropping the variables that contribute to highly VIF value. Okay, so how to detect a multi-quality? We can use variant inflation factors measurement, and when we perform, if any variables that have VIF greater than 10, we can conclude that the variable might contribute to multi-cognitive problems. Okay, so you can consider to remove, but Again, this is the remediation that can be taken if multi-cognitive problem occurs. You can do nothing if it does not affect the model's performance, or you can drop the offending variables and choose the one with the least theoretical support. It means that even though that you have x1 and x2t, it seems that there is not the theoretical justification for x2t is weaker compared to s1t, like our previous example. So you can drop x2t instead of x1t. Or another else, if you increase the time period, and you can solve the multi-cognitive problem, so you don't have to remove any variables. All right. So that's about a general explanation on statistical validation and testing procedure. And we will continue showing you on how to forecast using econometric in R by performing the model selection strategies, okay, based on statistical validation. Okay, so this will be continue on next video. All right. So thank you for listening. Bye.